Hello student, how are you? Hope you are good in this time of pandemic. So today we are going to be discuss about the very important terminology or topic, you can say, the Hooke's law and stress and strain curve under this particular subject, strength of materials. So let's start with that. So some important terminology we are going to be discuss on that. What is the elasticity and elastic limit? So elasticity is that a property of a body, a material by virtue of which undergoes deformation when subjected to an external force and regain its original configuration. Configuration means what? The size and shape under the removal of the deforming external force, which is said to be a elasticity. Simply you can understand. So any material you apply the external load. Once you remove that external load, if the material regain its original shape and size, so this is called the elasticity of of that particular material. So for example, you can say if you take the rubber band and you take it just stress um, and when you apply the load, you remove your external load, then it's regain its solution. So you can say the rubber band is elastic materials. So dear students, so now let's understand what is the stress setup at that point. So what is it called it? So the stresses corresponding to limiting value of the external force up to the within which the deformation defect will completely upon the removal of external force is called the elastic limit. So that as simple you can understand. So at that maximum amount of the load up to which if you remove that load and body it is able to regain its original shape. So that limit, at that limit, what amount of stress setup on the corresponding to the limiting value of external force, that is called the elastic limit. That's it. A material is said to be elastic if it is written its original position, original shape, unloaded dimension. Okay, when the load is free. So before applying the load, what were the dimension? If it is a material begin that is said to be that material is the elastic material. So if external force is a large, then stress exceeds the elastic limit and material loses some extent its property of elasticity. If now the force is removed, the material will return to its original shape. Then there will be residual deformation in the setup inside the material. So second term is the Hooke's law. So you can say Hooke's law, you might be studies in the physics at 11 standard. So Hooke's law said when a body is loaded within elastic limit, so stress is proportional to strain. So suppose stress we can say denoted by the sigma. So stress is proportional to strain, or this is E is denoted as a strain. So with this law, say so within the elastic limit, this stress is proportional to strain. Okay, so within the elastic limit, the ratio of within the elastic limit, the ratio of stress upon this developed strain, that is a constant, and that constant is called the modulus of elasticity, which can be represented by the capital E. So also it is called the Young modulus. So simply you can say, my dear students, sigma upon is equal to E, and where already in the last class we discussed that the stress is equal to load upon cross-sectional area of this material, and what is the strain we have studied, that change in length upon original length. And so we can directly write E is equal to how, what will be PL upon A del L. Del is the change in the length. So simply you can calculate the Young modulus if you have these four terms. So you can able to calculate the Young modulus using this formula. So dear students, this is about the Hooke's law, and you might be got this concept. This is very simple, very 5. So Hooke's law, elastic moduli, simply that we are trying to make you understand. So if that is the modulus of elasticity for the steel, so that is 210 gigapascal for steel, and likewise for the aluminum 70 gigapascal. Other material also has their some respective value of Young modulus. So in the same way, you can convert modulus of rigidity, where tau is the shear stress and s phi is the shear strain. So also with the use of that, you can calculate the modulus of rigidity by using the Hooke's law. And factor of safety, this term you will be studying the more basically when you are going to study the design subject. So now just understand what is the factor of safety, the ultimate stress and the permissible stress. So how ultimate stress we are getting from dish, the tensile test, and permissible a material having their strength. So this by dividing these two factors, ultimate upon permissible stress and ultimate a factor of safety very important before taking the design. Let's coming up, we'll discuss more on that. So what is the stress and strain? A simple tensile test I can must say. And whatever going to be the is about the stress and strain, this curve can be obtained by performing the tensile test in the universal testing machine. In the lab section, we will discuss on that. Okay, so you can say my the right hand side, you can say this is the specimens, and this is the intact specimen before performing the test, and this one is the after the test and material is break or fractured. So the both type of this is taken. So this kind of failure occur in the brittle material, and this cup cone type of failure will occur in the then with tactile materials. So this broadly you can understand here, and then during the experiment you can better understand that. So standard tensile test involve a circular bar of uniform cross section, gradually increasing the increased tensile load until the failure occur. We are increasing gradually loading with the help of Newton machine, and we perform this test. And tensile is carried out to compare the strength of various change in the length of a selected gauge length of the bar is recorded by the extensometer. Extensometer is basically used to find what is the final change of the length of the specimen. But we can also calculate before measuring that. We can suppose we make a gauge here, and initially we measure, and after what is after what is simply we can use using the vernier we can calculate it also. Okay, so graph is plotted between load and extension and between the stress and strain. So this is the simple stress and strain diagram for a ductile, which having the ferrous on the ductile ferrous materials, and ferrous material is a ductile material. So it's come under the category of ductile, but which having the ferrous inside, the content of iron. So this is a specimen. You just pull out an axial with the help of UT. So when gradually we are applying the load up to this is called the limit of proportionality. So material exhibit the linear in nature. So this specimen is just proportional to up to that point A. Then B is called the the limit of elasticity, and C is the upper end point, D is the lower end point, E is the ultimate point, and F is the fracture point. So these silent points which have their significant meaning. So right there is what happens? We are applying this load. So this is the gauge length we are assuming. This is the cross section area. So up to A, no problem. You stress up to A, and you leave the load, material will regain its original point. So this is this up to this the Hooke's law applicable up to A. But point B is the twice point of elasticity. So problem is that it reach to the point of elasticity. So some stresses are set up in that inside the material, but for the calculation, what we are assuming that both are coincide. So we are taking actually the elastic limit up to the B for the calculation. Okay. So now we discuss about the point C. What is the point C? Is the upper end point. Yield means that first metallic bond break at this point, and they are further breaking the material metallic bond, then when you are continuously gradually then again apply the load, so what happens? So there is a, in the crystallisis the stress hardening is happening. So what to get that much of deformation you have to be apply higher load, and that is a higher load at point E. This is the maximum load. That's why it is called the ultimate stress develop a corresponding to this organ ultimate point. So after the ultimate, you have to be apply the less load to get that much of deformation. So this is the simple stress strain diagram where you can understand different salient feature, where the salient point have their significant meaning. So up to this is called the this is the elastic limit, elastic deformation. Okay, after that, after this to this is a gradual plastic deformation, and this is the total plastic deformation. So you can see significantly you can understand this type. So let's move different meaning of different point. I already explain you what is the meaning of that. So no need to explain again. So you can better understand with the hysteresis diagram with this diagram. You can see this diagram. Initially, specimen there is no load. This is called the baseline. This is a no load condition. When you load apply, the material is stressed up to what here. Okay, but this is called yield point state. If you remove, so it will regain this one again. So it is reached to this, and beyond that, if you are again apply gradual load is applied, so then what happened? Then it is reached the maximum point, and after the maximum point, this position basically here, this necking, this neck formation is started at this point. Okay, this is point the ultimate tensile strength also, and this necking will start from this point. Okay, after the fracture. So after the necking, and if you again, if you continue application of the load, so that the material will be finally fractured. You can say the uniform plastic deformation, non-uniform plastic deformation, elastic deformation. This is the different zone here. So you can understand elastic strain develop, plastic strain develop. Okay, so total strain is like this. So we can calculate here. If you calculate the slope of this slant line, so you will get the Younger model directly stress under the strain. You will know that the stress corresponding to this represented stress, and this is one strain, and this is stress. So you can simply calculate the slope up. We can calculate the slope up. So any point we can get the Younger modulus of with the help of this curve. So simply the steady state curve for non-ferrous material. So if the material is ferrous, so you have to perform tensile test like this. If the material is a non-ferrous, but material is a non-ferrous, but material is a ductile material. So that material is a ductile, but it's not ferrous. So this kind of material is not exhibit clear cut yield point. So for that we are using a method 0.2% offset method by drawing in this. So we can directly obtain, because gradually we are apply the load and material break here, and we really need to be young. We need this young yield point. Without yield point, you can't be design. So all the design what we are making any kind for machinery or element on the we are considering this stress yield point. So yield point is very important. So what we are point is, so what is 2 point option method is say, so what the amount of strain develop here, you just multiply by 2%, matlab 0.002 on suppose it's their strain is 0.01, and you multiply this, then what value will come? So you just measure here and draw a parallel line to this initial line where it is cut to the curve. This point is can be represented as the yield point of this particular material. So non-ferrous ductile material, aluminum. This is for the aluminum. So for the aluminum, you can use 0.2% offset method to get the yield point. Might be you are understood. So it can be very simple. You can this length you already know total length multiply by this. This need to obtain parallel line draw by this. You will get. So OA as the A point represent the yield point. So simply for the brittle material, the good thing is that there is no clear cut of exhibit its exhibit the yield point and ultimate point. So you can say the both yield point, ultimate point are same at the fracture, all the existing at the structure point, which when the load is applied continuously, it's increasing at that point, it's become, it's gradually, it's a break, no necking, no ultimate point. So this we can say the strain at the time rupture is smaller for brittle ductile material. So this for when you are dealing with the brittle material, so your what design you are making, so you are considering this breaking is breaking strength of the material for design. So hope you have understood this concept. So thank you so much for being here listening.